Testing?
Yes.
Okay, now you can open your PowerPoint.
Okay. Can you see my screen there?
Hold on, we are just checking it.
That's why we need to look at it.
Yeah, it's atmospheric conditions associated with deep compression in the macro sea, right?
I can hear you.
Scheme.
You can hear me?
The one you use for things like
Perhaps we need to hang up the phone call.
Yes,
When I
sure.
saw previously, it's mainly because of the skin is big.
Okay.
Everything there is
but it
big.
shouldn't be that different.
Two.
That's what I thought. Actually, it's the bottom of the rocks actually the car 3 points.
So can you see my slides?
Hold on, we are just forwarding your mail again.
Use the surface layer to calculate the
So you've already seen that, the difference.
yeah, because
When I am using something, I don't know. Yeah, it's a title page right now, right?
Yes.
Okay. All good?
Can I go on?
Still on the title slide.
Like wrong. Instead of around 1.5 months, it gives
Everybody knows how can we bring it to the screen on the browser.
increase the whole domain.
No, it's only portion of the part of the right? Do you know how to bring it to the screen? Yeah, also, but it doesn't
For now, these are these are social
Everything is only change to the wrong black hole and then
没有
we saw that it should be
Is everything good? Cool?
Huh?
Is everything okay?
Yeah.
Okay.
So actually, I want to go home.
Shall I go on?
yeah.
Yeah, you can start.
No matter
Okay. Hi.
they should
Something's going on there? Or?
Yeah.
Hello?
Go ahead.
Okay. Hi, everybody. So today's topic of my talk is the atmospheric conditions associated with the deep convection in the Labrador Sea, which is collaborated by Steve Yeager and Gökhan Danabasoglu here, Ankar, and of course Ping Zhang. And outline, I'm gonna first talk about the case study of the 2007 to 2008 winter, which is just submitted to GRL paper, and later I'm gonna show some results from the generalization case for this study for the period of 1950 to 2009. And let me first highlight the Labrador Sea first in terms of ocean circulation and climate. Lab Sea is perhaps the only region in the world where oceanic deep convection persistently occurs in the open ocean. So, can you see my arrow?
Yep.
Yes.
Okay. So this map shows the North Atlantic Ocean. So Greenland is on the top of the map, and Lab Sea is still west of southwest Greenland and east the North America continent. So you can see this. There's not much of topographic feature around Lapsea. So the Lapsea is directly connected to the broader North Atlantic Ocean. So, the foaming deep water foam in the Lapsea can easily spread out into North Atlantic. So this source water is considered as the source of North Atlantic circulations, such as AMOC and Sopala Gyre, and associate heat transport variability on Decatur timescale. And the Lapsea is also where freshwater from Arctic and subtropical origin waters and sea ice and storm tracks meet. So there is great complexity there. So it is considered as one of the tipping points under global warming. Of course, for an onset of deep convection, you should have very low stratification there. So, for example, this left panel shows the density profile in the Lapsea. Black is in November and red is March. You can see in November there's still substantial buoyancy in the ocean, but you don't see much buoyancy in the March. And this buoyancy existing in November should be eroded by the surface fluxes or lateral fluxes, but for the case of Labrador Sea, is dominantly eroded by this surface heat flux. And this surface heat flux is highly correlated with the North Atlantic Oscillation, which is the dominant atmospheric pattern in the North Atlantic in the winter. And you can see this right panel shows the temperature, blue, and salinity properties of Labrador seawater, which is the product water of deep convection. You can see there's a strong correlation between this Labrador seawater properties and NaO, which is the sign is reversed here. So the red is positive and the blue is negative phase of NaO. So when you have positive phase of NaO, you can see this strong cooling in the Labrador seawater. So this diagram simplifies this relationship between the NaO and the other oceanic processes. So when you have positive NaO, there's stronger westerly over the Lapsea, which brings the cold air from the Arctic. So there's a greater heat release in the Lapsea. So there will be deep convection. So part of this anomalies recirculate around the Sopala Gyre, so which enhance the Sopala Gyre strength, and part of this anomaly propagate further south into the subtropics, so that enhance the overturning circulation, and that will bring the heat into the Sopala Ocean. And this kind of relationship is clearly shown in fourth ocean simulation. The right panel shows again the NaO index. Now is the sign is right, so positive is up and negative is down. And the below panel is from Core 2 project. So in this project, the 19 ocean model is forced with the same same force in Core 2. So in this plot, the red is Labrador Sea mixed depths, and black is AMOC strength at 45 north, and the blue is the barotropic stream function average over the entire Sopala North Atlantic. So you can see there is a strong positive NaO trend from around 1970s to mid 90s. So you can see such a positive trend in the mixed layer depths, and also the barotropic stream function, which is in strong pace in negative value. So downward trend means here stronger subpolarized strengths. And also you can see there's a similar temporal evolution in AMOG as well. But after this strong positive pace in the early 90s, the NAO is kind of a neutral state, especially after 2000 winter. But so the deconvection is more or less does not happen in the LAPC after 2000. But suddenly in 2008 winter, deconvection returned. You can see this return of deconvection in the right panel, which shows the buoyancy frequency from the Argo profile. So the bluish color means the weak stratification. So in 2008 winter, you can see very weak stratification in the LAPC. But in 2007, NAO was even stronger, but the deep convection or just convective activity is just as low as the previous winter. So in this Baga et al. Paper, although they highlight the complexity of LAPC, but they speculated this deconvection with the colder temperature than 2006-07 winter occurred because of this well-organized storm track, which is shown in the red lines in these below panels. But if you look at closely, this black shading is the frequency of the storm frequency instead of the track. You can see the frequency is lower in the LAPC even than this winter. So this raised the question about their results. So we first look at this daily time series over the LAPC in 2007 and 2008 winter from CORE, which is based on the ANSAP with some corrections based on the satellite or in situ observation. And the top panel shows the turbulent, the sensible plus latent heat flux, and the second is surface air temperature, and third is winds, and fourth panel shows the wind speed. The surface heat flux is in 2008 winter much stronger surface heat flux than 2007 winter. Here the heat flux is positive upward. And this stronger surface heat flux is associated with the cold temperature in 2008 winter. If you look at this surface winds, this cold temperature is associated with this predominant westerly. This red line is Jonah winds, so positive means the westerly there. But if you look at 2007, the air temperature, especially during this period, is much warmer than the climatological air temperature, which is shown here, dashed line here. And this warmer temperature is associated with the much weaker westerly, or, well, I would say easterly regime during this period. Oops, sorry. And well, if this warming event or warmer condition in 2007 is associated with the synoptic storms, then you may expect a higher wind variance in 2007 winter. But both either U and V separately or wind speed, both wind variance are equal or stronger in 2007 winter than 2008 winter. So I don't see any reason this colder condition in 2008 winter is related to the storm activity there. So next I look at the spatial pattern of this atmospheric conditions in 2 winters. The top panel shows the sea level pressure winter mean anomaly with respect to 2000 to 2007 mean, and the middle panel shows the surface air temperatures, and bottom panel shows the 2 to 8 day band pass filtered free variance. And you can see in 2007 winter, the atmospheric condition is similar to NAO pattern, which is shown in the left, but the Icelandic low, or the Icelandic low, is shifted to further southwest. So there's the strong pressure gradient also shift to the southwest. So there's not much pressure gradient over the Lap Sea. And 2008 winter, the pattern is not like NAO anymore, and the pressure center is located in the western side of North Atlantic. So there is a stronger pressure gradient over the Lap Sea, because the pressure centers are located in the western part of the North Atlantic. So you have colder air temperature in 2008 winter, but you don't have that cold condition in the 2007 winter. And you can see from this zonal wind variance, in 2008 winter, meridional wind variance is even weaker than this 2007 winter over the Lap Sea. So this 2008 winter, the deep convection event in 2008 winter looks associated with the large scale atmospheric pattern, which is quite different from the traditional NAO pattern. So this arrows here shows how people measure the NAO. The black arrow shows the traditionally measure the NAO. So when you measure the pressure difference between Iceland and Azores around, then, which is the traditional definition of the NAO, you don't see much of pressure difference in the 2008 winter. But in fact, the pressure gradient over the Lap Sea is very strong because the pressure center is shifted to the west. And next, we further confirm on the findings. We did numerical experiments using core to force Popp-Heincast model. Popp is 1 degree global ocean general circulation model coupled with a sea ice model, which is ocean component of CASM and CASM coupled model. This Heincast simulation shows a lot of good agreement with observation in terms of several metrics. I want to highlight here the 2 aspects. First, this Heincast simulation reproduced 2008 deep convection quite well. The right figure shows in the upper panel shows the mixed layer depths anomaly in 2008 winter in Heincast simulation, and to the right, this is from Bage arrow from observation. So shading is 2000 to 2007 mean, and this triangle is the mixed depths in 2008 winter. So if you can create the plot-like model, then I think the pattern would be very similar to what Hindcast simulation show. And the second thing is the level of the seawater variability in Hindcast agrees really well with observation, and this bottom right panel shows the left sea average density from 150 to 1,000 meter from observation, black, and red from Hindcast. So you can see at very low frequency, the agreement between two are very good, indicating the Hindcast simulation simulate good variability in deep convection or deep water formation in the lab sea. So we first took the I didn't talk about much of the oceanic preconditioning part. I will show later. But we first, if there is a special in 2007, November 2007, or prior to 2008 winter, then if we use this ocean initial condition forced with 2007 forcing, we still have this deep convection. But when we use this ocean initial condition with 2007 forcing, then the deep convection anomaly is not pretty much there. This is consistent with the stratification anomaly in November 2007. Actually, there is a weak stratification in prior to 2008 convection season in the northern or eastern Labrador Sea, and which I think related to this anomaly here. But the strongest anomaly located in the southwestern Lab Sea, so this is not related to oceanic preconditioning. So next, in the next experiment, we kept the initial condition same as the 7IC, 7F case. And we replaced the winds from 2007 to 2008. So which is basically 2008 simulation with 2007 air temperature and specific humidity. And the mixed depths anomaly is still much weaker. Yeah, and I think even weaker than this 7IC, 7F case. And next, we did the same experiment, but with the air temperature. And now you can see this strong deep convection anomaly in the lab sea. So indicating the air temperature is played a great role in this event. And the wind does not play this role. And next, we add specific humidity in addition to air temperature. And we have even stronger now mixed depth anomaly. And next, we further decompose the air temperature into low and high frequency using 30-day low pass filter. And in this experiment, we only changed the low frequency part of 2008 air temperature with the high frequency of 2000 air temperature. Then we almost recover this experiment with the whole 2008 air temperature. of course, the other case didn't show much of a mixed depth anomaly. So conclusion of this case study can be summarized like this. So the deep convection event in the 2008 winter returned with the large-scale atmospheric conditions centered in the western North Atlantic. It's quite different from the conventional NAO pattern, not directly associated with a change in storm tracks. And measuring atmospheric variability in the eastern North Atlantic, which is the traditional definition of NAO, may not always explain the atmospheric variability in the western North Atlantic. Now, I'm gonna generalize a little bit more using the full period of core forcing, which is 50 to 2009. So left panel shows the composite pattern for sea level pressure, top, and air temperature for when left sea heat flux is greater than 1 standard deviation. And you can see the pattern is, well, similar to NAO, but definitely you can see this second maximum in the western North Atlantic, and also this Icelandic low is shifted to the west a little bit compared to NAO pattern. This right panel shows the same composite when NAO is greater than 1 standard deviation. And you can also see this wind vectors here, which is wind vectors greater than 3 meters per second. The stronger wind is located in the left sea in this case, while the strong wind is located further east in this NAO case. This plot shows the NAO index bar and this heat flux in the left sea, the red here, and you can definitely see first, which is they are correlate highly, but you can see this in these years they don't agree well. For example, 1972, NAO was almost neutral state, but heat flux is very strong, and same happened in also 84 and 91. So I take a look at what the pattern looks like, and in all these years, pattern, the sea level pressure pattern is similar to what we see in 2008, centered in the western North Atlantic, and the wind and air temperature anomaly is also consistent with the 2008 pattern. So I look at the first 4 EMF first, whether this anomaly can be explained by this widely used EOF analysis. First pattern is NAO, and the second is the Scandinavian pattern, which is centered in the Scandinavian and the over the Greenland or west of Greenland. And third pattern is Eastern Atlantic pattern, which centered in the west of England. And well, PC4 force mode centered in the western North Atlantic, and it explained very small. I mean, the total variance only explains 7.1%, but if you look at the associated anomaly like air temperature and the heat flux, then you can see there is a substantial loading in the lab sea associated with this pattern. Well, we can also think about the combinations of these patterns. For example, the center is the NaO, and if you combine NaO with this force mode, then you can see the shift of the center to the western side, and you can even have this center with this second mode as well. And if you combine first, second, and fourth, then you have this kind of pattern. And if you combine, if second and fourth mode is strong enough, then you don't even need NaO to generate stronger pressure gradient over the lab seat, like shown here. And this, let me skip this part. In fact, this 1972, 84, 91 is some kind of combination of between Scandinavian pattern, second mode, and the fourth mode. For example, 1972, NaO was neutral, but Scandinavian and fourth mode is strong, so you can see the pressure gradient over the lab seat. And 84, which is a little different, and in 84, NaO and the Scandinavian pattern was almost neutral, but fourth mode is very strong, so you can still, only with this fourth mode, you can still see this strong pressure gradient and cold air temperature heat flux. And 91, also the combination of these three with the stronger contribution from Scandinavian pattern. So it is obvious if we need an index for the lab seat variability, we need pressure gradient in the western side of the North Atlantic. So just an example, I mean, if you take the pressure difference between two regions, over the Greenland and over the where is it? This is close to Newfoundland, I think. Yeah. Then the right panel shows the correlation between this index and heat flux. That's AMOC times is in red, and the black shows the correlation between these with the traditional NaO index, and you can see substantial increase in correlation with the new index. Was like 0.7 with the NaO, but now it's close to 0.9. 0.7 before and 0.9, and 0.7 below than 0.7. Now it's 0.8 for mixed depths, and of course, you can still have an improvement in AMOC correlation too. So this NaO and the first to third pattern is relatively studied more, but this fourth mode is, as far as I know, there's no paper discussing this pattern, and we don't even know whether this is physically real or not. So I tried to find what's this pattern, whether it's real or not, something like that. The first top panel shows the global northern hemisphere sea level pressure pattern regressed onto this PC4, and you can see this high pressure over the northern Europe and something like that. And I also regress SST onto this PC4, and I have quite substantial SST anomaly in the Central Pacific. Right, yeah, Central Pacific. And the right panels shows the results from a study, Latnam et al. So in this study, they took this central SST anomaly and superimpose on the climatological SST cycle, and they force the ocean, the atmospheric general circulation model, and this pattern is what they have, which is very similar to this PC4 pattern. So looks like this pattern is related to the Central Pacific El Niño or Modoki, and yeah, that's it. Sorry. Yeah, this is summary. Surface heat flux variability over the lab sea is associated with the NAO-like pattern, but with the second pressure center in the western North Atlantic, which is explained when considering second and fourth mode of the North Atlantic's level pressure together with the first mode. In particular, the fourth mode plays an important role, which appears to be related to the Central Pacific elite. The end.
Yes.
Questions?
So this is all oceanal events, right?
Yes. Well, with sea ice.
Yeah. So how do you initialize the model? Which data set?
How initialize a model?
Yeah.
It's initialized the Levitas climatology, but because I started this sensitivity run only for 2007 or 2008 winter. For those sensitivity runs, the ocean was initialized with the existing hindcast run, so control run. So as I explained, where is it?
So otherwise you just start with Levitas density structure.
I'm sorry?
Otherwise you just start with Levitas temperature and salinity.
Wait, the velocity too. So sea ice condition, temperature, salinity, and everything from the November 1st of 2007 is used to run the sensitivity runs.
Okay.
I don't have a question, but I have just a comment.
Okay.
This is with respect to the last part, the ENSO versus the PC4.
Okay.
So as you pointed out last week in my presentation about LabC heat flux response. So I done some kind of a similar composite analysis on that. Those responses I have separated. So essentially, what I did is so the aerosol response. Essentially, what I did is I made a composite of when there was a very big response over tropical Pacific versus when there was not much response over tropical Pacific.
Okay.
I made these two composites, and I could see that when I'm considering a bigger response over tropical Pacific versus when there is not much big response over tropical Pacific, I could see the heat flux, which was the enhanced heat flux response over the LabC also changed. It went away in one of those composites. So it must be related to some way. At least it's consistent even with. I think it's consistent with what you are finding here.
Okay. Great. Can you send me the plots you have with the explanation?
I can do that.
Okay. Thank you.
That's pretty interesting.
Yeah.
Central Pacific and Labrossi.
Yeah.
Do you have any methods to check the time scale? You know, who comes first and because in a composite you can't say anything about time, right? Yeah. So
So I
If
don't.
you, instead of the composite, if you have one isolated event which is pretty strong,
Mhm.
you can start looking, before the anomaly pops in, and then see, which is causing.
Yeah, I can do that. Only thing is, the only disadvantage in those things, they are just like 1 year, 1 year.
Yeah.
So that's the problem. That's the problem. But yeah, it's still, it's very consistent. Like I just did a composite when there was a bigger response over tropical Pacific versus when there was not. And I could see the lab C's. In one case there was a greater heat flux over the other case it was not.
Any other questions?
No question?
Remote.
Remote
Okay.
remote participants. Chris, do you have any questions?
I'm sorry?
Chris, do you have any questions?
Oh.
No.
Okay.
Chris, I think you done an experiment with this kind of SST pattern, right?
Sorry, so I tuned in partway through, but I've done some experiments with AMM patterns, so warming in the northern tropical Atlantic or cooling in the southern tropical Atlantic.
Really? I thought you have the Pacific one too, no?
Oh yes, and in the Pacific as well, but mainly in the tropics.
Okay. Any, you don't have any comments on this thing? Because honestly, I don't know much about this El Nino and the atmospheric response. So, and even if this regression coefficient is quite strong, I mean, the correlation is like 0.3 or something. So, and Dr. Chang told me the people's gonna argue this PC4 about the PC4 because which explained too small and we don't know whether it's real or not. So, if I want to make a link between this Central Pacific SST, the atmospheric pattern over the left seat, then do you have any suggestion what should I do or something?
I'm sorry because I only tuned in partway through, so I don't know if I completely followed. But are you actually at NCAR now?
Yes, I'm at NCAR now.
Okay, so I'm going to be visiting in a week and a half, so maybe we can talk then.
Week and a half, which is
the end of this month.
Okay.
April 27 and 28.
Oh, that's great. How long are you gonna stay here?
Just the 2 days.
Oh, okay. Yeah, just can email me or something when you arrive here.
Okay.
Yeah.
All right, then. Thank you.
Thank you.
Okay, just wait for a second. Can you please stop? And then on the stop menu, you can hang up the start.
Okay, stop.
Oh, no.
No?
Stop broadcast with the
Okay.